Hey everybody, welcome. I'm Chuck Schembri. I'm with the Nevada Department of Environmental Protection. I'm an environmental scientist and a soil scientist. And today we're here in Carson City at Fuji Park, and we're going to do some of my favorite soil health presentations. We're going to be doing a slake test and a water infiltration test, or some people call it a rainfall infiltration test. These two soil tests are a great demonstration to look at healthy soil properties versus unhealthy soil properties, and to understand the function of soil under the forces of water. And so what we're going to see in the slake test, we'll start with this one, is when soil is put into the water, the soil is going to, the pore space is going to get filled with the water. And a more healthier soil has strong soil structure, it has strong aggregate stability, and the individual soil particles are more tightly glued together through biological glues or biological cementing agents. And we're going to look at two soils that are the same soil type. I'm going to pick them up here. They're both sandy loam soils, Nevada soils, not too far from here at the Reno Experiment Station, which is managed at the University of Nevada, Reno. And these soils were provided to us from the Desert Farming Initiative. And these two soils are about 800 feet apart in two different fields. They both have been farmed for decades. And what I have here is a soil on the right, is a soil that was under permanent pasture for quite a long time. We know many decades. And then it was recently converted to intensive cropping system under regenerative farming practices. So that means very minimal tillage, a lot of residues left in place, minimal disturbance, cover crops, and high crop diversity. This soil on my left is a soil that was under a lot of different cropping systems for research, predominantly conventional farming, so a lot of tillage, a lot of chemical application for controlling weeds and pests. This soil still, there's some chemical application, but it's all organic and generally, organic biological fertilizers. This soil was a vineyard for about the last 20 years, and a lot of mechanical disturbance, just a lot of disturbance in the soil, no soil health principles implemented, so no cover crops, no residue management, and again, quite a bit of tillage took place in the soil. I'd also like to point out that you can see the difference in the color. This soil is darker and this one is lighter. Again, same exact soil texture. They're from the same geological landscape or geomorphic landscape. This soil has over 4% organic matter, and this soil has less than 2% organic matter. So what we know about these two soils is, well, one, this one is by definition healthier. It has more pore space, it has much more biological diversity, more biological activity. So it has much more biological glues or cementing agents, which binds these soil particles together and creates what we call strong soil aggregation or good soil structure. This soil has much less biodiversity, a much unhealthier soil microbiological population or less. Again, it has less organic matter, so it has less of the biological properties we want to see. If you want to conduct this soil demonstration, you can do it anywhere. You can do it in your garden, you can do it on the farmland. Again, these are agricultural soils. What's important to showcase and illustrate the properties of soils under the forces of water is that they must be completely air dried, or you can oven dry them at a low temperature, about 100 degrees. But essentially, soil is composed of around 50% of soil is pore space. And so what we've done is we want the pore space in here to be pretty void of water, or water that's available for plant uptake. So we have very, very dry soils here, so you can assume that the pore space is not occupied with water. So when we put these soils in the water's immediately going to begin filling that pore space. And if it's a healthy soil, then the pore space is going to, its integrity is going to be, and structure is going to be maintained, and water will be able to fill into that pore space. A soil that doesn't have as strong of aggregate stability or pore space, as much pore space, we'll see that the water can't really fill this pore space, and we may see pore space collapses. So we're going to see that during this demonstration. This soil is going to be much more easily eroded than this soil is. So the slake test will illustrate this for us. So I've kind of given away already what you might see, but we'll let the soil speak for itself. Okay, so I'm going to invite my volunteer friend Martina up here to help conduct this slake test. So we're both going to pick up our soils here and we're going to put them in at the same time. And also wanted to point out, we have these PEDs, we call these soil PEDs. They're about the same size. So when you're doing this demonstration, we want to have the soil PEDs be roughly about the same size. Okay, you ready to put it in?
Yep.
All right, let's do it. You can just push it in all the way. Okay, so we let the soil speak for itself. I already explained a lot of what you might expect coming into this this demonstration. Now let's think about this in the field environment or in the natural environment. You can see this soil here on my left, the one that is less healthier soil. The soil particles are detaching from each other. They don't have the biological glues that are bonding them together and all of the other biological complexity, hyphae and fungal hyphae and other fine root systems that are going to keep it intact. Doesn't have good porosity, so the pore space is literally collapsing as the soil particles detach. And so these soil particles, now that they're detached and they're in solution, if this was say a storm event on agricultural lands or a big irrigation event, or non-agricultural lands where there's very disturbed soil, these are the soil particles that are leaving the site through runoff or even wind erosion, because although we're looking at water, some of these principles still apply to wind erosion. And these are sedimentation is our largest water quality issues in the United States and probably across the planet. These soil particles are also carrying with them other nutrients, residues. Soil is really good at bonding to particulates and chemicals, especially clay soils. Here on the right, boy, we barely have had anything fall off, or we call this the slake test because what we're looking at here is these particles are slaking off of each other. They're slaking apart. And we look at the soil on the right here. The pore space is being filled with the water. The soil particles are not collapsing. As I mentioned, the soil has much more organic matter and the biological glues and the cementing agents to keep the soil intact. There is a little bit of soil breaking and slaking off on this one. That's natural. Soil erosion is natural. This is not necessarily natural though. This is, we could say it's a human-induced phenomenon to have soil erode at such a high rate. So from a water quality perspective, I think it's clear and evident. We let the demonstration speak for itself. We have turbid water here that's in a rain event or a storm event or irrigation event, transporting soil particles to water bodies. And on the right here, we have very clear water that is obviously much better water quality. Okay, now we're going to conduct another soil health demonstration test known as a soil infiltration test. Soil infiltration tests can be done many different ways. Obviously you can do it in the field, but for the sake of demonstration in classrooms or on in-field trip environments, we have this nifty setup here. Basically just have two cylinders with a top that we're going to pour water through that's perforated. And at the bottom of these tubes is perforated as well. It looks like this. So we're going to pour the same volume of water over the top. We're going to watch it rain through, and we're going to see how quickly the water infiltrates through these two soils. We also have we're using the same water volume, and we have a green and a red water so that you can easily see how quickly the water is infiltrating through these cylinders. And again, we have the same soil types as we used in the slake test. We have on the right the healthier soil. It's got more organic matter, more regenerative practices and soil health practices being implemented, more biology. And then on the left, we have the soil that doesn't have as good of soil health properties. And as we saw in the slake test, the soil on the right slaked apart very quickly. It wasn't as resilient under the forces of water. So when we pour the water over, we will see which one can infiltrate water more efficiently than the other. Okay, Martina's gonna come and help me out again. I'll let you come to right here this time. She gets the red water, the bad water. Okay, so we're gonna pour this over the top, and we can just do it just nice and casually. It's the same volume of water, so it doesn't matter how fast we do it. We'll just make sure nothing can fall or spill. We'll also be able to see how much water is percolating through this soil profile. I forgot to mention the soil was broken up a bit. It has to be to put it in here, but soil properties are microscopic to the microaggregate level. So again, we'll let the soil test speak for itself. Well, I think it's worth talking about now. We could wait another hour for this to drain through, percolate through, infiltrate through the soil profile, but as we can see, the healthier soil on the right, much more efficient at infiltrating water through the soil pore space. On the left, as we saw like in the slake test, when those soil particles detach, the pore space collapses. And so what we have here is on the top, the particles are actually collapsing and subsiding and creating a sort of the way concrete forms, you can imagine. So the surface is being sealed off because these soil particles aren't being held together through all this biology that's maintaining the structure, the aggregation. The pore space is collapsed, and so it's not able to allow the water to infiltrate through the topsoil. But on the right here, obviously all the water drained through very quickly. Because the soil has more organic matter and more pore space, it's actually retaining more of the water as well, which is kind of hard to imagine in this demonstration because it looks like it all just poured right through. Now, one of the most important implications for a farmer and the watershed is this water in a healthier soil, it's infiltrating and it's having deep percolation into the subsoil and into the groundwater. So we can assume that we can have better groundwater recharge and also more subsoil moisture for the growing season. Okay, this water we're keeping on site. You have a little bit of slope on your property. This water here that's on the top, it's already moved off site. It's running off. And as we saw in the slake test, it's running off with soil particles. That's going to the stream. Okay, we're looking at the infiltration test here again to see the end results and the impact to the soil surface. So looking down here, we had the rain droplet impacts that hit the soil surface, and the soil particles are detached from themselves and sort of coalesce and subside, and creating a seal to the topsoil. That's what you're looking at there. You don't see any soil structure or much aggregation, and that's a typical view of a sealed soil surface. And now we're looking at the healthier soil in the soil infiltration test, and we're gonna take a look at the topsoil of this one. What you're gonna see is different properties here where we can see the aggregates, we can see the structure and complexity of the soil. It didn't subside, there wasn't all the soil particle detachment. And we don't have any sealing of the soil surface, so you still can see that complexity and structure of the soil. It's very important in any climate, but in particular in Nevada, we want every single raindrop from the sky to stay on our site, right? so we can use less irrigation during the growing season, so we can recharge our groundwater, so we can have more long duration of seasonal flows. All right, guys, we've seen the soil slake test, and we've also seen the infiltration test. Now we're going to be conducting a rainfall simulator soil demonstration test, which sort of combines the two. So in this demonstration, we can look at runoff, we can look at soil erosion and water infiltration rates from two different managed soils. So in this soil demonstration, we have two soils from a farm in Fallon. The fields are separated by not much of a distance, you know, probably a quarter mile or less. And in the soil here on my right, we have a no-till corn system which integrates winter cover crops in the winter, triticales and rye and other legumes. And the residues are left in place. I'm going to lift this up just so we can get a better look. The residues are left in place during the winter, and it is a no-tillage system. And then the soil here on my left, this is an alfalfa field that is a pretty typical alfalfa field. The farmer's starting to implement some different techniques and soil health practices. And so it's probably relatively a healthy soil. We're not saying one is more healthier than the other. We're just going to look at today the differences of having this residue and a no-tillage system with corn versus this alfalfa, which is technically a no-tillage system. Probably is rotated every 4 to 5 years, so there is some mechanical cultivation happening. And we have much less ground cover and residues through the winter on this soil here. So we're going to pour water over the top to simulate rain. This is the rainfall simulator, and we'll see what happens. Now I'm going to invite my trusty volunteer back up here, Martina, to help me mimic Mother Nature. We're just going to pour the water over the top here. This is perforated. They got the same perforations, and so water is going to run off and collect in here, and then we also should have some level of infiltration through the soil profile, and we'll look at how much water makes it into, call it the subsoil or groundwater. Okay, Martina, you ready? All right, here we go. Again, we let these soil demonstrations speak for themselves. Thank you, Martina. Well, we haven't done this yet, and I wasn't sure what to expect. Okay, so let's talk about what we see now. From the no-tillage corn system, it's been under no-tillage for 5-6 years or so. If we just look at the water clarity here and how much water ran off, obviously we have more clear water from here, and from this alfalfa that had less residues through the winter, we had more soil exposure, so the runoff brought with it more sediment, more soil and other organic material off the site, which would run off into our streams and other water bodies, lakes, etc. So we let it, it's pretty evident. And we also see, if the camera is picking this up, hopefully it is, less water quantity in here and more in here, so more water runoff, probably more velocity and flows coming off the land. Now the next thing we're going to look at is how much water collected into these basins underneath, and so this is representing infiltration into the subsoil, maybe into the groundwater. So we had more infiltration in this here, in the no-tillage corn, and doesn't look like we got much water that infiltrated through this soil. We'll take a closer look at this. Okay, so we've seen how much water ran off these two soils. We saw how much infiltrated is collecting in the basin. We're going to take a little closer look at that, but the next step of this demonstration is we're going to flip these over and we're going to look at how much moisture do we have at the bottom, or the lower in the soil profile? How much water infiltrated through? We can see that in these little catchments, but we'll take a closer look at this by flipping. Whoop, that one wants to come out right away. Okay. Try not to shake this table. All right, so let's take a look here. Probably no surprise. I think we can tell a lot more moisture in the subsoil, if you want to call that the subsoil. We'll pretend this is a 3-4 foot pit, right? Look at it on the sides. Much more moisture in the subsoil here, especially that view right there, ladies and gentlemen. You can see essentially where the soil stopped infiltrating, and more of it ran off, of course. I'm going to lift these up here so we can get a good visual of how much water infiltrated through these soil profiles and collected into our catch basins. Much more water here, much less water here, no surprise, right? We poured the same volume of water in on the top. We had more runoff from the alfalfa soil and less runoff from the corn. No-till corn system. So this is a great demonstration for looking at soil erosion, runoff off of the site, and water infiltration. So what are some healthy soil practices you can do at your home or on the farm? Well, there's 4 principles to soil health. Well, some say there's 5, but we'll start with the 4. There's minimizing disturbance. So that can be reducing tillage. It can be reducing synthetic chemical inputs to the soil that might cause issues to the soil microbial biology. We also can keep our soil covered. So that means covering it with plants, or covering it with residues or mulch. So residues are something we talk about residues on a farm, because instead of tilling everything under, we're trying to keep as much of that biological material, the plant material, on the soil surface to keep it covered. Soil must be protected. If you're in a forest environment, if you're anywhere in the natural ecosystem, Mother Nature keeps the soil covered. It does not want the sun to hit it, and it does not want the wind or the elements of the atmosphere touching the soil. So keep that in mind. How much can I protect my soil? Number 3, a living root system. So living roots, that also can apply, or that same principle can be applied to having keeping the soil covered. So we keep the soil covered with plants, but ultimately we want a living root system. The roots play a huge critical role in the function of soil, feeding the biology. We won't get into the full science of root systems, but a living root means we have a plant, and plants are photosynthesizing, pulling carbon out of the atmosphere and feeding that carbon into the soil, which is so important for soil health. And number 4 is biodiversity. We want to create as much biodiversity on our farm or our garden, or even in a forest environment as we can. So again, I'll mention the 4 basic soil health principles. Minimize disturbance. Keep your soil covered. Keep a living, continuous root system as much as possible. And number 4, have as much biodiversity as possible, or plant diversity. And number 5, which a lot of people believe is a strong soil health principle now, is integrating livestock. And they mean that in a holistic way of integrating livestock onto the landscape. Ruminants have been on our planet for thousands and thousands of years, and have played a real critical role in the health of ecosystems. The Native Americans, we know, used a lot of ruminants like buffalo and elk and deer to their advantage on the landscape. So integrating livestock can be a really great tool. Again, I'm Chuck Schembri with the Nevada Department of Environmental Protection. I really hope you enjoyed these soil demonstrations today. If you're looking for any technical assistance or advice for your education program, feel free to contact me at my contact information right here. And I'd love to work with you in your programs and get you guys set up to educate the public or farmers in your community.